This is some pretty interesting stuff also. The applications of it are where things really start getting fun. But the concept of partial integration, it's like, I understand that this looks very intimidating, right? And actually, as you thumb through this packet, if you've already had a chance to take a look at it, you see things like spherical coordinates and so like, ooh, scary stuff. It's really not that bad because it's all grounded in stuff that we are very familiar with at this point. And partial integration, I mean, when you think about partial derivatives, what did we do? We held one variable constant and we differentiated with respect to the other. So we're just going to do the same thing, but in the reverse, all right? So when I find the antiderivative with respect to y of this multivariable function, all I'm doing is pretending that x is some constant, all right? So if that is the case, then this would just become a 2xy, all right? 2xy, because there's an understood y to the 0th attached to it. You're just increasing the exponent by 1 and dividing by the new exponent. Plus 1/3 y cubed. The only thing you have to bear in mind is that, yeah, we're integrating, which means that you have some integration constant that we call c. All right. No subscript necessary because it's just one integral. If you remember when we were dealing with, well, actually, I'm going to amend that in a second. You could just leave it as a c, but there's also another way you could represent it. But when we were dealing with vector valued functions, we had to distinguish one constant from another. This is not the same idea, right? Now, c could be some constant numerical value, but it could also be some expression that is just made up entirely of x. So what we could say instead, and again, I'm prefacing this by saying I don't really care. If you put plus c, that's good enough for me. You could say plus c of x, all right? Because this allows for any, so allows for any expression containing an x. All right, because if we're treating x as constant, then technically, I mean, I could add anything onto the end and it would still be fine as long as it's made up exclusively of terms involving x. So let's say, for example, I said my final answer was 2xy plus 1/3 y cubed plus the sine of x. Well, sine of x has a derivative with respect to y that's equal to 0, so that would check out. All right. So a little bit different, but nothing too crazy. So the other case, we're taking the antiderivative with respect to x. So we're looking at x squared plus y squared x, all right, because the y term is being treated as a constant. And then we would add c to that, but we could technically say c of y, because this allows for any expression containing y. Jeez, this pen just took a walk on me. All right, allows for any expression containing a y. Now we get to the juicy stuff. Now you remember earlier in the course I said that anytime you have a definite integral, you could just pop it in your calculator and call it a day. And we're all thrilled about that because in a lot of cases finding a definite integral is, you know, it's aggravating because if you know that you can easily get the answer just by putting it in the calculator, why do we have to do all this work? Well, usually at that time I say, yeah, I let you off the hook with that because we make up for it with other topics. There's plenty of work to be done. So what does it matter if we do this one thing in the calculator? All right. So hopefully I said words to that effect. If not, I apologize. All right. What's going to happen here is, well, there's no double integral function in your graphing calculator. So you would not be able to just type this in. So what we can do, though, is kind of limit the amount of work that we have to do by hand, because we work from the inside out when we find a double integral, or triple integral, or quadruple integral, also known as iterated integrals. So an iteration is really just taking an answer to an operation and plugging it back into the operation to recompute, all right, and doing that repeatedly. All right, so what we're doing is we're getting this answer and then substituting it back in to the expression to continue the process. All right, so what I'm going to do here is I'm going to figure out this definite integral by hand, and then the rest of the way we'll be able to do it on the calculator. All right, so with respect to y, we're looking at 1/2 xy squared plus 1/4 x squared y to the 4th happening over the interval of 0 to 2. All right, so I'm just increasing the exponent of y by 1. So y had a power of 1, increased it to 2, divided by the new exponent. Same deal for the other one. I'm working around the x's, all right? So I'm not concerned with the x's. Then what I'm going to do is plug in. Now this again is with respect to y. So this 2 and this 0, these are for y. All right, so y is equal to 2, y is equal to 0. Now the 0 is not going to be relevant because I plug in a 0, that's going to go away. But if I plug in the 2, we'll get some unique values. So I plug in the 2, I get 2x plus 4x squared. All right, so that is my result for the first integral. Now all I want to do is integrate that with respect to x over the interval of 1 to 3. So you can see here that by carrying out the first integration, I now have a function that's exclusively in terms of x. Now it's calculator ready. All right. Now, granted, it's not. I mean, it's polynomial. You know, it's not difficult. You can do it by hand, but you don't want to have to do it by hand. All right. Especially since there are some problems that they could technically involve some pretty complicated stuff. I mean, we went over trig substitutions. That was one problem. It involved trig substitutions and also integration by parts. It was that one time, it was like a month ago, when we started the problem in class and it involved a secant, and I was like, okay, I'm gonna stop here and we'll pick up with it next class, because it took forever and we were kind of right at the end of class, right? It could be like that, but it doesn't have to be, because the first part of the problem, really, if you think about it, it's just a matter of working in terms of one variable, right? And so one of the tricks that I'm going to show you, a little trick of the trade, is kind of really cool. Is that if the arrangement of dy and dx is not to your liking, I'm going to show you how you can legally swap them. All right, you could switch the dy with the dx. There's a particular technique involved, and if you do that, you might make it for a more convenient integral. Something that maybe you would not be able to integrate prior to, but afterwards maybe you can make it very easy to integrate. All right, but as it stands right now, I can do this one by hand or in the calculator and not have any trouble whatsoever. So I just got to get my calculator out. So, I resume. So again, just a reminder, it's Math 9. We're typing in a 2x plus 4x squared on the interval of 1 to 3. All right, so 42 2/3. You can write it like that if you want. the math bracket, 128 in the, over 3. Didn't involve radicals, so math frac was an acceptable option. All right. So basically, it's kind of like I don't know how much you remember about synthetic division, rational roots and stuff like that, but I kind of compared this idea to that, where when you were working with synthetic division, your whole goal was to get it down into something that you can solve without using synthetic division, like a quadratic. You could use the quadratic formula, for example. Here, it's the ultimate goal to get it down to a single integral so that you can get away from having to do stuff by hand. All right, so you're just buying yourself time until you can just pop it into the calculator. So in the case of number 4, you look at that and say, well, okay, I got to do 2 things by hand. All right, because I got to integrate with respect to x first. It's always inside out. Now, if you're rightfully wondering why on earth we're doing this, like what's the purpose of this, stay tuned, we're getting there. All right. So here I see that I have a function contained within the innermost integral that does not contain a single x. That's beautiful. Because when I integrate this, the z sine of y, the integration is just that multiplied by x. Now that's happening over the interval of 0 to this disgusting looking 4 minus z squared. But regardless of how disgusting it looks, it doesn't have, it's going to replace the x within the function. So x is going to go away in a sec. All right? It's just things are going to get a little kooky. All right? So this is going to end up being, I'll write it in the cleanest way that I can, z root 4 minus z squared, and then that whole thing multiplied by the sine of y. All right. So then we're integrating this over 0 to 2 with respect to z, and then we're integrating that result over 0 to pi with respect to y. All right, so we haven't learned under what circumstances we could swap the variables. So at this point, we just have to grit our teeth and just get it done. All right, so, because this would be a lot easier if I could integrate with respect to y before I integrate with respect to z, because this would serve as a coefficient. Antiderivative of sine of y would be negative cosine of y. That would be nice. But unfortunately, the parameters are not in the order that I'd like them to be. And we haven't learned how to do that. And so we'll come back to this problem later on after I show you how to swap variables. And we'll revisit it and I'll show you how it could be a little bit easier. All right. But until we get into the visual aspects of this, there's no point in talking about it because it's not going to make any sense. Not a failing on your part. It's just I can't make it make sense without getting into the visual stuff. All right. So I'm going to rewrite. This guy over here is the same as saying z times 4 minus z squared to the 1/2 power. Now that sine y is going to be part of my final answer, or part of the next step in my answer, I guess. All right, because that's treated as a constant multiplier. All right. So this would be a U-substitution problem, but I like to at least try to do U-sub on the fly. The idea being that if I could save myself from having to define a U, to just rewrite an expression, to basically come up with an answer that I probably would have guessed to begin with, then like why not just take a shot in the dark? Right? So I know that 4 minus z squared to the 1/2, because U-substitution is really just the shortcut to undoing the chain rule. All right, so if I were to find the derivative of an expression using the chain rule, then 4 minus z squared to the 1/2 would probably be in that. So what I'm going to do is anti-differentiate that part of it. I'm sorry, to the 3/2. So 4 minus z squared to the 3/2 power. All right. So then what I would do is just kind of test this out and see where it gets me. All right. So if I differentiate this, it would become 3/2 multiplied by this to the 1/2 times the derivative on the inside. All right. So, and you could just kind of scratch this out off on the side somewhere. You know, if I were to take the derivative, I'll just kind of chuck it over here. 4 minus, I'm going to erase it in a minute anyway. 3, just to kind of give you a look into the thinking behind it. I'd be looking at 3/2 times 4 minus z squared to the 1/2 times negative 2z. All right, the 2's would cancel, and my coefficient would be negative 3z times all that other stuff. I'll just rewrite it. All right. Now, none of this would be happening on paper for me. This is all happening upstairs. All right. So I'm just thinking, well, I don't want a negative 3z. I just want a z. All right. So what that would mean is that the coefficient of this integral, this result of the integration process, should be negative 1/3. All right. So, and that's just a correct for it, because I needed to get this, I got that, I want that to go away, so just multiply by negative 1/3. Right? So I can wipe out all that stuff, because that's all just side scratch work. Right? Because the reality is, if you're going to do any work for an integral, you might as well do the appropriate U-substitution. The thought process behind that is that, you know, you take a shot in the dark, see if you can come up with what the antiderivative would be, and then go from there. And if it doesn't work, then that's when you call it quits and move on to you know, a different technique. All right. Now this is happening over the interval of 0 to 2, which is just wonderful news. All right. Well, yeah, it's news again. Maybe it's not wonderful news. It's just news, because the two works out beautifully. If I plug in a 2, it's going to 0. All right. It's just in this case, when I plug in the 0, it goes to, well, potentially something else. All right, because we're integrating with respect to, or we integrated with respect to z, so that's the only thing we're substituting in for. All right. So all I have to do is plug in the 0 for z, and I'll get my results. So sine of y, it's subtraction of a negative, so that's going to a positive. 4 minus 0 is 4, to the 3/2 is 8, so we're looking at 8/3, right? So sine of y times 8/3. So the last, that should be a pi. The last integral we have to count for is the 8/3 sine of y with respect to y. And that you can even do by hand, because like I said, working with trig functions, that's specifically sine and cosine, that's super easy, barely even. Right? So I'm going to get sued for using that comment over and over again. So negative 8/3 cosine of y on the interval of 0 to pi. All right, so negative 8/3 cosine pi minus negative 8/3 cosine of 0. So we're talking 8/3, because cosine of pi is equal to negative 1, plus 8/3, because cosine of 0 is equal to positive 1. So result is 16/3. right. So that's one funky looking iterated integral, but conceptually there's nothing new there, right? So it's just a matter of carrying out the process. And the only sticking point is actually finding the antiderivative in for the second iteration. Once you do that, it's home stretch. And I only opted to do that last bit by hand. You just pop that right in the calculator and get 16/3, it comes out clean, right? It won't always come out clean, but I accept decimal answers anyway, so what does it matter, right? Exactly. Now, number 5, I'm exercising my teacherly right to do all the easy ones in class and then leave a hard one for you to do on your own. All right, so I'm putting a star on that one. And again, just like the other Lagrange problem, it's only for the purpose of you giving it a whirl first before I take you through the process. All right. What I have now, just looking at the relationship between dy and dz, I have the ability to swap these because these correspond to a rectangular region. All right, this part of it, the x, that doesn't seem to be relevant because we've already accounted for that by the time we get to this step. All right, so when we're in this step here, we could have actually swapped the dz and the dy only because this corresponds to a rectangular region. And how do I know it's rectangular? Well, these are constant values. I'm going from a z value of 0 to a z value of 2. All right, so those would be two parallel lines. All right, we're going from a y value of 0 to a y value of pi, so two parallel lines. Intersect them and you're going to have a rectangular region. All right, so what I can do now is I can go back to that problem as promised, and we can swap the boundaries of integration same function, so z root 4 minus z squared times the sine of y, but this time I would make it, instead of dz dy, I would make it dy dz. All right, so that allows me to just integrate this mamma jamma here. All right, so when I'm integrating this part, I don't need U-substitution or anything even remotely complicated. I'm just integrating the sine of y, which is negative cosine. So I'm looking at negative cosine of y times z times the square root of 4 minus z squared over the interval of 0 to pi. So once I crunch those numbers, things are going to start cleaning up very nicely. And then we'll be done with the problem in seconds flat. All right, because if I plug in a pi, I'm going to get a negative 1. So positive 1, so just z root 4 minus z squared. Plug in a 0, I get a negative 1, so minus the negative variation of this. Which is going to give me 2 of those, so 2z square root of 4 minus z squared. And that's happening over the interval of 0 to 2. Now you might say or think, wait a minute, I still got to do U-substitution, but you're neglecting the one critical component of this. Once you get it down to a single integral of one variable, it's a calculator problem now. It's no longer a by hand situation, all right? So, I had to use substitution. And if it wasn't as simple as that, then maybe I would have had to do something else, like partial fraction decomposition or something crazy. Here it's the same type of integral, same difficulty level of integral, but now I have the ability to use my calculator. So swapping the boundaries, incredibly not only useful idea, but also in a lot of cases necessary. And what I always do, and this is something I could definitely back up because I've done it already. instead of making those the promises that I don't always remember to cash in. So anyway, math, enter. I always put on the test a 16/3, much easier. Right? I always put a problem on the test where it's impossible, at least from our perspective, based on the knowledge that we have, impossible to find the antiderivative one way, but very easy to do it the other way. Right? So it's one of those where if you try to work with it in the given form, no way you would possibly get the result. But when you swap the variables, and it won't be a simple case where the base region is rectangular. When you swap the variables, it becomes very easy, like very, very easy. Instead of describing it, I'll just show you. Digital link. Blurry. Huh. I'll bring it in. Alright, so number 7 on the previous version of this test had the iterated integral where the innermost function was the inverse sine of y. Alright, so what happens is people try to fake their way through this solution, and in some cases they actually think that they know the right answer, because what happens is they get the derivative and antiderivative of inverse sine confused with one another. So if you remember that the derivative of the inverse sine is -1 over the square root of 1 minus x squared, or in this case y squared, congratulations, it is of no help in this situation. All right. That's not entirely true, because if you know that fact, you could use integration by parts to help you figure out what the antiderivative of that is. But you can see I have a variable upper bound here, so another technique that we're about to learn comes into play. But if I'm able to swap dy and dx, now this is just treated as a constant. Its antiderivative is x times the inverse sine of y. At which point, chuck it in the calculator, call it a day. All right, so you go from something that would take like an entire page to do, you go from that level of difficulty to something that's like, I can't believe I ever thought this was difficult, right? It's that much of a disparity between the two ways, right? So I always put a problem on there like that, and it will be number 7, right? So the way the test is structured, you know, I put 2 versions up because I had a really large class in the spring and a lot of people with rolling eyes during the test. I had like a solid 35 people in the class, and there were a bunch of people that were like clustered together, and they were trying to share answers, but you know, you get them a couple of times when they copy down the answer to the wrong version of the test. You know, it's always nice to see. But yeah, so I have 2 different versions of the previous unit test for this unit. So definitely plenty of opportunity to practice. But you can see, you know, a temperature function, a little gradient action. You know, you got that bad boy right there. You got some volume questions. You know, you got a proof. So definitely something you can even start working on it now, because if the first one's a directional derivative, absolute max and mins, we've worked on that already. Critical points on second derivatives test, Lagrange. I like saying that, as you can probably already tell. This is the gradient question. The volume stuff we're not ready for. After class today, we'll be ready for any kind of iterated integral. But basically anything that involves volume and area, we're not quite there yet. But you can start making some headway on this. You know, so definitely something to keep in mind. All right. So, continuing on. So now we're going to talk about the why as opposed to the how. And actually, we're going to kind of get into the idea that you've been working with double integrals for a long time already. You just haven't realized it. All right, so that's kind of a strange thing to think about, because it's like, how on earth could that be the case? Because I have never seen that double integral symbol before. Yeah, I've taken the antiderivative and then taken the antiderivative again, but that didn't mean what this is about to demonstrate that it means. All right, so we'll see. Now, what a double integral gives us is actually, and you look at the Riemann sum variation of this, is giving us the volume over an interval, right? Areas and volumes, depending on what you're looking at. So if you look at the diagram, basically what you're getting when we find the product of dx and dy. So the notation here is a little bit, I would say, on the noisy side. So let me just kind of streamline it a little bit. Right? We're looking for infinitesimal length and width. Right? So what we have here is some function that we'll call z that has a height. All right? So that's my z function. Then we also have some length in the x direction, infinitesimal length. So we call that dx. We also have an infinitesimal length in the y direction, which we call dy. All right? So what we're getting at here is that the volume contained between a three-dimensional surface and the xy plane would be z, it's length times width times height. So it would be z multiplied by dx by dy. All right? Or the other way around. All right? You could say dy dx.
So it could be like z could be like a function for like a wave, and you can figure out like the volume of like the waves on the ocean.
Exactly. Yeah, so as long as you have a function that represents the surface wave, like what it would, the path that it would be traced out on the surface, then you could figure out the volume over a square interval or square region. All right. So what we figured out is one rectangle with infinitesimal width. All right. So I can sketch this out a little bit. Yeah, it's not quite in my wheelhouse, as we know, but it's something. So we would have this rectangular prism. That actually wasn't half bad. All right, this rectangular prism, I mean, it's drawn with thickness, so it makes it seem like it would actually be like a matchstick. But it's really not. It's of such infinitesimal dimensions that it would be imperceptible, right? Or imperceivable. I don't know what the right word is. Anyway, so what we would have to do is collect every single one of these infinitesimal distances along the x-axis. And we do that by integrating. All right, if you learned anything about Riemann sums back in Calc 1, it was the idea. Now, there's a lot of hand waving in Calc 1 related to it, because it's just it's a concept that people don't often enjoy teaching, so they kind of skip over it a lot. But the origin behind the integral, the definite integral, comes from the collection of all of those infinitesimal distances. All right, so if you're looking for area, you find a little teensy tiny sliver of a rectangle, find a function model for that teensy tiny sliver of a rectangle, and then integrate all of those rectangles together to give you the collection of total area. All right, so that's what we're going to do here, but we're going to do it for both the x dimension and the y dimension. All right, so I would need a double integral. All right, so an integral to account for the x dimension and an integral to account for the y dimension. And z, I don't need infinitesimal distances, because what's going to happen is, as we project those infinitesimal x's and y's up into the z, it naturally creates the sliver of z that we need. For each one of the x's and y's, we get a corresponding sliver of z. Right? So we don't actually have to manufacture that. We could just use the z function itself. Right? So the same idea holds if the order is reversed. So we get to our first real connection here, and that is that if you have a square, or sorry, not even square, rectangular base region, then the order of integration is irrelevant, right? So that's telling me that if my rectangular region, or my base region, so the region corresponding to the surface, but on the xy plane, if that's a rectangular region, then it doesn't matter if the dx comes before the dy or vice versa. It's when it's a non-rectangular region, that's when we have to do something different, all right? So in the case of that previous example, so basically everything on this page is really just addressing what I was just talking about. All right, so it's a lot of textbook jargon with really not much payoff. All right, so I'm going to take you through an example, a juicy example here. And if you look, I mean, I don't know how, it's probably not that good on your papers, but the traces of the graph or the wireframe is often more useful than the actual shaded version of a surface, right? So you can kind of get a sense of the parabolic nature of this curve here just by looking at the wireframe, right? So, like, what's that?
Actually came out.
Oh, it did. All right, cool. Every now and then, you know, a broken watch is right twice a day. So what we want to do is find the exact volume of a solid bounded by the surface given. And then we have a rectangular region, a rectangular base region. So that tells us that we're going to be able to swap our boundaries. Our variables of integration. All right. So, but what we want to do is start to develop a little bit of an intuitive understanding of why on earth we're doing this to begin with. Right? Because what I've experienced both as a student and as a teacher is that for this particular topic, as well as volumes in Calc 2, that people start to kind of rely on, all right, here's a rule, I'm going to put in some numbers, I'm going to put in a function, I'm going to hit enter on my calculator and hope it gives me an answer that isn't ridiculous, and then move on to the next question. All right? We're trying to avoid that sort of thing here, and hopefully we can do that. All right, so we want to be parallel to the YZ plane. All right, I didn't really make that part of it as obvious as I could have, but here's my Y, and here's my Z plane. The Z plane is easy enough. All right, so parallel to the YZ, so we're talking about this corner here, so this surface. So basically anything that follows this orientation. All right, so I'm going to use the wireframe to my advantage here. I'm gonna bring it in a little bit. I'm thinking I already have red. I'm gonna go with purple. I'm gonna go with red. Clean miss. Yellow? Yeah, red sucks. Back to the yellow. Oh, yeah. Oh, look at that. That's pretty good looking right there. All right, so I'll bring it all the way down, even though this is not actually how the graph would look. I'm going to bring it all the way down and create a little slice. And that slice is going to have some thickness. This is related to the technique of finding volumes by cross sections in Calc 2. And so we're going to kind of rely on some of that knowledge. All right. So the topmost part of it, I'll shade it in. All of this bit of stuff here That's all along the surface. All right, so this is on the surface of the function. All right, so its height is determined by whatever the function is. So I'm going to just call that z. All right, the thickness is along the x-axis. So that's going to have a thickness dx. All right. So if I want to find the volume of this whole shebang here, all I would need would be a length y. All right, so that's going to be going from the x-axis out to whatever that value of y is. It's hard to see, but I think it's 6. So that would correspond to this distance here. All right. So what I would be looking to do is multiply y by dx and then multiply that by z, and then we would pretty much have it. But the issue is I can't actually multiply the entire dx by just a y, all right? Because what's happening is I have little infinitesimal distances here that are going out along the y-axis, all right? So collectively they give me that distance y, but each one of those little slivers, and I'll just draw an arrow to one of them, I guess, would be a dy, all right? And so what I want to do is collect every one of them, because remember, I mean, and drawing the diagram is a nightmare, but if you think back to the previous page, we had those rectangular prisms that ended up giving us the volume. So what I'm looking for is a rectangular prism that has dimension dx and dy that projects up into the surface, the edge of the surface. All right, so each one of these little slivers we could think of as a dy. If we collect them all together, then I would have my function. All right, so what I'd be looking at is z dy, it locked me out, dx. All right, and that would be happening. So the y values, you know, I'm not going to scroll back up, but I think it's pretty straightforward. It looks like my y values are spanning from 0 to 6, and my x values are also spanning from 0 to 6. All right, so so if we collect all of the dy's underneath this curve, what that's going to do is it's going to give me a y. So let me show you what that looks like. So we carry out this process of integrating. That first calculation gives me just a zy on the interval of 0 to 6. All right, easy enough. All right, I'm not actually going to put the z in until I need to. All right, and I don't need to yet. All right. But if you remember, what I was saying before is that what I wanted to do was take that entire distance, that horizontal, well, not really horizontal, but you can kind of think of it as horizontal, depending on your perspective. But the distance along the xy plane parallel to y, we wanted that entire distance y, where y was equal to 6, because we knew that that was not going to change. But sometimes it does change, so we want to be flexible, all right? But ultimately, by finding the antiderivative, that's what happened anyway. By finding the integration or integrating z over the interval in terms of y from 0 to 6, we got z times y, which is precisely what we were looking for anyway. All right, so intuitively, that's what we would have come up with, but in the act of creating an iterated integral, it worked itself out. All right, and so what we get here is 6z over the interval of 0 to 6 dx. All right. Oh, sorry. Back it up. Just back it up. Just back it up. Back it up. At this point, we have to plug in the z function because z does have a y in it. We have to make that substitution. All right, so z is equal to x squared sine pi y over 6. Oh, dang. I needed to even substitute it in earlier. All right, well, I proved my point with the whole integration thing. Now I'm going to use a technique that I like to call the right way to answer the question. All right, so 0 to 6, the z, battery's low, it's one of those days. So again, x squared sine pi y over 6. So x squared sine pi y over 6 dy. All right, so maybe not as easy as I was making it seem, but we'll get there. All right, so integrating really only involves me messing around with this component because that's the only one that has a y in it. All right, so negative x squared cosine pi y over 6, but then I have to divide by the inner function, which would be the same as dividing by pi over 6, which is multiplied by 6 over pi. I liked it better when it was just a z. All right, so plug in the 6. We're looking at negative x squared, because it's still with respect to y, cosine of pi times 6 over pi minus, I'm going to do the same thing, but then I'm plugging in a 0. So negative x squared cosine of 0. Yeah, but we're dividing by the derivative of the inner function. So dividing by pi over 6 is the same as multiplying by 6 over pi. So we're multiplying by the reciprocal. If we were taking the derivative, we would multiply by pi over 6, but it would go in the other way. All right, so we're looking at, well, this is going to go to a negative 1, so we have 6x squared over pi. These two will become positive. So cosine of 0 is 1, so plus another 6x squared over pi, which is going to be 12x squared over pi, but I'm going to write it as 12 over pi x squared. All right, so then we just have to integrate that with respect to x. And so that you could chuck in the calculator, but you also don't really need to because, again, it's pretty clean. Because the part that was making it difficult was the presence of the trig function, but now that's gone. We've swapped it out for a constant multiple. So, and one thing that I would recommend, because we came across this, I think, last class, where if you leave the pi in there, then you're going to have an answer that's a multiple of pi, so you're going to get an ugly decimal. But if you pull out the 12 over pi, anti-differentiate, even in the calculator, let the calculator do the work, and then just multiply by the 12 over pi later on, you get a cleaner answer that way. But I'm just going to do it by hand. So x to the third, we're dividing by 3, so 4 over pi over the interval of 0 to 6. So we're looking at 6 cubed from my experience in statistics is 216 times 4. So we're talking 432, 6, 864? 864, yeah. over pi. So, you know, a fair amount of computation, but again, that last step didn't actually have to be done or completed by hand. It's just a matter of, you know, just picking and choosing your battles. All right. Now, if you go the other way, so you swap your variables of integration, then you should still get the same answer, but you're going to get a different diagram. Right, and so I'll draw the diagram, but I'll leave it to you to try that on your own. All right, so when I draw this diagram, I'm looking at something that would come across, you know, something like that. Now, I'm just kind of working off of what I have here. You know, it definitely goes up and has a maximum at some point, but you know, it makes it seem like it's chopped off at the top, but it really doesn't matter what it looks like on the high end. It's what matters is what it looks like on the low end. So we have something along these lines. Now I'm going to span out in the direction of x with each one of these representing a dx. All right, and here's my dy. So when I didn't get a y in there. And we definitely know that the height of the surface is going to be equal to z, some variable z. So what we can do is collect each one of these slices. So we did it with respect to y first. So now what I'd be saying is that I'm taking my z function, multiplying it by dx dy, and integrating the x component over the interval of 0 to 6, followed by the y component also over the interval of 0 to 6. All right, so that's your setup. All you have to do is just carry out the process, but don't do what I did. Remember to put the z, the x squared sign of whatever it was, in for z before you get started. Otherwise, bad things are going to happen. All right, so all of this is really just introducing what's known as Fubini's theorem. And it tells us that the order of integration is interchangeable, but not always easily interchangeable. All right, so if it's a rectangular base region, it's easily interchangeable. You just swap your boundaries of integration and you swap your variables. But if it's not a rectangular base region, then you got to do something different, which is the subject of the last thing that we're going to cover today. All right, so we're going to move on to that in a second. Let's do this real quick before I forget. So what if the region in the xy plane is not a rectangle? Funny you should ask that. So we have all these rules, all these fun rules, linear combinations of double integrals and all that good stuff. The linear combination stuff is really just telling us that just like with definite integrals in single variable calculus, you can break apart different bounded regions, find their areas and volumes, and then add them together later on. Right? You don't have to just do it over a finite interval. Right? So that I don't think is anything new. Right? I mean, to think about, but it's pretty easy to do. Right? But you could use the concepts that we've covered with multiple integrations to determine the volume, because if I draw just a rough sketch, very rough sketch, in 3 dimensions of a plane, so I'll just do obviously not an infinite plane, yeah, but you know, just some subset of it whose dimensions are s by s. All right, so I would be defining that area as s squared. then what I would naturally be getting by finding the double integral of this would be, I would be finding the volume contained between that function, that plane region, and the surface of the xy plane. All right, so this is y, this is x. All right, so as long as I have a way of representing that plane, then I'm good to go. All right, so it's got to be parallel to the xy plane, which means it has to be in the form of z equals. So z equals some plane that we're calling, well, we can call it anything we want, but if we're going to have a cube, then the length, width, and height all have to be the same. So the height off of the x-axis, xy-axis, has to be the same as those two other dimensions. So z would have to be equal to s. All right. Now, common sense tells us that, okay, you take the length, width, and height, and multiply them together, you're going to get s cubed, which is the volume formula. But we want to do this using double integrals. All right. And then later on, we'll use triple integrals, because why not? So what I'm going to do is I'm going to find the double integral of the z equals s, so just s. It's over a rectangular base region, so dx dy or dy dx, it doesn't matter. All right. Now, the boundaries of that. Now, the sketch is really helpful when it comes to this, because the boundaries for integration would go from the corner, which is at 0, 0, 0, to this intersection right here, which has to be s units away, because opposite sides, opposite edges of a cube are congruent. So this has to go from 0 to s. Same is true for the y. All right. So if I need to know what this corner is over here, then opposite edges of a cube are congruent. That also has to be s. So that's going from 0 to s as well. All right. So now I have my setup, and this will define the volume of the cube. All right. So v equals. So work inside out. S is some constant value, so antiderivative is sx over the interval of 0 to s, which is going to be s times s, which is s squared, minus s times 0, which is just 0. And then I'm going to take the antiderivative of that with respect to y. So same deal. S squared y over the interval of 0 to s, plug in the s, and you get s cubed. Plug in the 0, you get a 0, but that's all we needed anyway. Volume is equal to s cubed, and that's what we were going for. All right. So what that tells us is that for at least the cube, we could actually invent a geometric rule using our knowledge of double integrals. Right? So then it would naturally project out to things like, okay, what about a circle? Right? What about some other non-rectangular figure? You know, maybe an ellipse or something like that. You know, can we invent those geometric formulas just using the concept of the double integral? Right? Because really the concept is associated with your knowledge of finding an antiderivative. If you could do that, then basically it's eliminating any need to know geometry rules, right, for volume. Right? Same idea for area, because if I just cut this off at one integral, so not a double integral but a single integral, then I'd be looking at an area over an integral. Right? And in fact, it came out in the wash there. We get s squared. That's the area of a side of a square. All right? So area of a facet of a square, all right, or side of a cube. And so you get what you need out of this. So what if you had some funky figure that didn't have a defined geometric shape? You know, you could find its volume pretty, I don't want to say easily, but consistently. All right. Yeah. I mean, you'd have to come up with a relationship and, you know, define the the function itself, but you know, once you do that, you'd have it. All right, so now what we're going to be dealing with is the non-rectangular. Definitely not anything new. But let's hop on over to page 75 and tackle a case where we have definitely a region here where it's bounded by curves on the base area rather than linear functions making it a rectangular base area. Right. So we know that we have some function z. Now it's represented as f of x comma y, but that's okay. Z is equal to x squared plus y squared. We know that dx and dy is going to give us a product that when multiplied by z is going to give us ultimately the volume, all right, contained underneath the surface. A lot of this is just going to boil down to problem solving, because sometimes they'll want the area or volume contained within the figure, and sometimes they'll want the volume between the figure and the xy plane. Like in this case, it's saying bounded by the curves in the xy plane. So it's suggesting that we only care about the volume outside of the surface but above that non-rectangular base region, which is fine, because that's what a double integral gets us. It always gets us the volume contained between the xy plane and the surface that we're interested in. But if I wanted something like the volume contained within the figure, then what I'd have to do is something a little bit more complicated. I'd have to find the volume surrounding it and then subtract all the excess volume that I don't want. That's way more complicated and really a subject or a conversation for a different day. All right, so I definitely don't want to rush into that because it's a lot more thinking involved. All right, so what I want to do is set up my double integral. All right, so I have my z, and you know, pick your poison. It could be dx dy or dy dx, but once you make the commitment, you have to stick with it. So I'm going to say dy dx. So I'm going to go with a double integral dy dx. I don't need it to be that far away. All right, now my bounded region varies depending on where I am along that bounded region. Okay, so what I'm going to want to determine is what the relationship is between these two parabolas, because definitely they're opposing parabolas in order to capture that bounded region. So I'm going to need to find the intersection of those two. So I'm going to set the y function of 1 minus x squared equal to the other y function, x squared minus 1, and solve. All right, so I'm getting 2x squared equals 2, making x squared equal to 1, making x equal to plus or minus 1. All right, so now I know my boundaries for x, which is great. So then I'd ask myself, well, what are my boundaries for y? Well, what I'd want to do is take a look at my base region, but only in the xy plane. All right, so I'm going to draw a quick sketch. And, you know, drawing quick sketches is not always what people have in mind. You know, you just want to be able to jump right into a problem and start solving it, but a good sketch goes a long way. All right, so what we're dealing with here are two, like I said, opposing parabolas. If you remember from Calc 1, so this is y equals x squared minus 1. Y is equal to 1 minus x squared. If you remember from Calc 1, when you're finding the area between two curves, what we did was you took the dominant curve and you subtracted from it the non-dominant curve. So the one that was physically above the other. That's when you were looking from the perspective of the x-axis. But if it were from the perspective of the y-axis, it was the rightmost curve minus the leftmost curve. as long as there wasn't a change in dominance. All right. So here, the blue curve for the relevant region is always physically above the black curve. So we're in good shape. If there was a transition where the black curve was physically above the blue curve, like in the outer fringes here, then I would have to account for that, but that's irrelevant in this case, because I'm only looking for the region between the x value of -1 and the x value of +1. All right. So the difference between those two values would help me find the area. But really, all I just need to do is define my double integral based off of the lower function and the higher function. So the lower function of x squared minus 1 would go here. The higher function of 1 minus x squared would go here. Because it's physically higher, so it actually takes the higher location on the integral. So the one that's physically higher graphically is physically higher within the integral. All right, so it's going from, so in terms of y, it's going from vertically y equals x squared minus 1 to y equals 1 minus x squared. All right, and then the x values are spanning from -1 to 1, and so now we have our double integral. All right, so if you're dealing with a non-rectangular region, you have really two integrals that you're going to be dealing with. The first integral is the one that should contain the constants. The second one, well, the one that you would do first would be like the one that you would write the second. That one should be the variable function, or the bound should be variable. So the outermost integral should be the one that contains any constants. So it's kind of like a composite function where we're saying that y is equal to x squared minus 1, y is equal to 1 minus x squared, where x is equal to -1, x is equal to +1, or anything in between. All right? So with that in mind, we can go through this process, but you gotta be cautious, because if I got it backwards, then what I would do is I would create too many constants within the double integral too early, and it would mess everything up. And we'll talk about why that happens the way it does next class, but it has serious consequences. All right, so my double integral is going from -1 to 1, then x squared minus 1 to 1 minus x squared. The z function is x squared plus y squared, and we're integrating with respect to y first and then x after that. All right, so we're looking at x squared y plus 1/3 y cubed over the interval, so this is where things get weird, x squared minus 1 to 1 minus x squared. But all we have to do is substitute those functions in everywhere I see a y. So x squared times 1 minus x squared plus 1/3 times 1 minus x squared cubed minus all that same stuff, the same structure, just this time replacing the y's with x squared minus 1. All right, so minus x squared times x squared minus 1 plus 1/3 times x squared minus 1 as a quantity cubed. And you're like, this is outrageous. Why are you doing this to us? It's because I don't like you. No, this is a wonderful class. I actually enjoy this class. It's just, it is what it is. Look at this. It's terrible. Look at all that. That being said, it's really not as bad as it could be, because we succeeded in our mission. Our mission was to get down to a single integral that contains only one variable. So regardless of the fact that this is as ugly as sin, it's still something that could be typed into your calculator. All right? You can clean it up if you want, That should be a minus. No, it should not be a minus. I just got to close parentheses. All right. So this is something that could be typed directly into your calculator in order to get your answer. All right. That's the whole point behind this, is that we just need to do enough work to get it to be calculator friendly. And then once we do that, it's all good. All right. So that being said, I don't want to have to type that into my calculator, so I'm not gonna. All right. So what I'm gonna do instead is pop a nice little juicy star on number 5 there, and leave that for you to try on your own also. So that's where we're gonna leave it for tonight. But the skills associated with number 5 are exactly the same as what we were doing in number 4. It's just you're kind of changing your perspective a little bit, but it's not difficult. All right. So that, as they say, base region. So we tackled an example, and I left you to do one on your own. So we'll look at that together. All right, so compute the double integral of the function bounded by the curves x equals y squared and y equals 2 minus x in the xy plane. All right, so the double integral is going to be of the z function, because again, this is the same as saying z. Shutting off on me. d something else. That's the thing, because I don't know yet if I want to go dy dx or dx dy. We're going to kind of let this situation play out a little bit. All right. So it's bounded by the curves x equals y squared, which is a sideways parabola. Okay, so I'm just going to draw a quick sketch of that. A sideways parabola that opens to the right. All right, because three-dimensional graphs, they kind of get a little crazy. You know, you have the consistency of knowing that the x-axis is pointing towards you, the y-axis is pointing towards the side, and the z-axis is going up. But that doesn't mean that you could easily rotate this stuff in your mind. Sometimes drawing the sketch is the way to go. All right? The more experience you get with this, the easier it is to just kind of visualize it. All right? But we have a sideways parabola, and we have a linear function y equals 2 minus x. 2 minus x has a y-intercept of 2 and a negative slope, so you're looking at something along these lines. All right. So this is my base region. All right, that area bounded between those two curves. All right, so what I want to do is, well, I want to figure out where those intersections are. All right, so I want to figure out where the intersections are, and then from there, I want to define my boundaries based off of that information. All right. So the first integral in your double integral, or at least, I mean, because that could be weird. The first integral, you're right, is not the first integral you work with. All right. So this is my first integral. This needs to be defined in terms of functions. The second integral, the one that you would work with second, is going to be defined in terms of constants. Now, we'll get to triple integrals, but in a triple integral, it's the first two integrals have to be defined, or the two bounds have to be defined in terms of functions, and the last one is defined in terms of constants. So it's always the outermost integral is the only one that's going to be represented in terms of constants. All right, so it's never going to be the first integral that's like this number to that number, like -2 to 4 or something like that. If there's going to be numerical bounds, it's always going to be the outermost integral. All right, so when I find this intersection, what I'm really finding is the bounds for the leftmost integral. All right, so I have x equals y squared and y equals 2 minus x. So I can just use quick substitution. Y is equal to 2 minus y squared. All right, because x and y squared are the same. It's quadratic, so bring everything over to the same side. Or at this point, actually, just go to the calculator. Let the calculator do the work for you. I mean, it's a quadratic. It's easy enough, but, well, let me rephrase. It should be easy enough, but I showed you an example earlier of how I could make a quadratic very difficult. So, not on purpose. So I'm putting it in as x's, but still it's going to give me what I'm looking for. So graph it, and then use your second trace option 5 to find your intersection, unless it's something that's obvious on your table. You know, if you look at the table and you see something really painfully obvious in terms of an intersection, then just go for it. You know, because you could just scroll up and down. I see -2 for y values, common y values, that corresponds to an x value of -2. So that's one solution. And 1, 1. So the y values of -2 and 1 satisfy this. So I didn't have to do anything fancy like second trace or use the solver or anything like that. It's just a matter of looking at the table. Alright, so second graph, take a look and see if there's any matching y values. Alright, this stuff can be tricky enough as it is. I don't generally go looking to make the bounds these disgusting numbers. I think they're generally going to be pretty reasonable. Alright, so now I know that my outermost integral is going to go from -2 to 1. But what I need to do is define my innermost function, my innermost integral in terms of functions. All right, so those outer bounds are in terms of y, all right, which means that when I find my second integral, it has to be a dy, which forces the other one to be a dx. All right, so what I need here are x bounds. All right, so looking in the x direction on this graph that I sketched, you can see that the bounds are variable. They're not constant. So it's not just going to be a simple matter of plugging in two numbers and calling it a day. Because if I did that, you know, like what if I'm over here? Let me do that in blue. If I'm over here, I could say, yeah, these are my bounds. 1 and 3, for example. I don't even know. But, and then over here, 1/2 and 2.5. 0 and whatever. You know, all of these differences are just that, different. All right, until they're not different when you get right to the endpoints. All right, so each one of these, if I were able to find all of these distances, then I could find the integral for each one of those one at a time and then add them all up. All right, so you just think about what this is conceptually. A double integral is actually doing that. It's finding each one of these slivers of distances over this interval and then integrating them together. So each one of these distances corresponds to a height, which gives you a sliver of volume. The second time you integrate, when we do it from the y value of -1 to 2 or whatever it was, it's collecting every one of those slices, putting them together to give you the total volume. All right, so that's great. What it's telling me is that I got to find a variable expression that represents these x bounds. Well, I know that this linear function, which we were given as y equals 2 minus x, could be written as x equals, x equals 2 minus y. And the other function, well, I'll write it both ways. We have y equals 2 minus x equals 2 minus y. And then for the other function, we have x equals y squared and y equals plus or minus root x. So we have the ability to solve each one of them for y or x, depending on our needs. So then what we do is we look at what we have and what we need. What I need is a function defined in terms of x. All right. So out of everything I have available here, I have two ways of representing the line, and I have two ways of representing the parabola. I want the ones that are defined in terms of x. All right. So what that means is that I need this guy, but then I need this guy. All right. What's that?
I thought the curve would have to go from x.
Oh, sorry, I highlighted the wrong ones. Thank you. So what I need are this one and this one. I try to, even when I'm going in the wrong direction, go in that direction boldly. But yeah, it's got to be an x-defined function, right? So we just want to go from, because when you're dealing with y's, you're going bottom to top. For x's, we're going left to right. All right, so the leftmost function is x equals y squared. So I'll do that in red. And the topmost function is x equals 2 minus y, so 2 minus y. All right. It's kind of weird to think about it. It's like, oh, I needed a function of x, but I have a function of x, it's just x equals something in terms of y. All right, but then you think about like what this is going to give you. So when I integrate this in terms of x, it's going to introduce a new variable x to my integral. But then I'm going to substitute these bounds in for that, which is going to make my new function exclusively in terms of y. So that when I integrate that in terms of y, I can now substitute these values in for y. All right. So basically, it's what kind of value do you want to be accepted into your function in the second integral? All right. I want a y value to be accepted into my function. So whatever you do in that first integral process needs to create a new function that is in terms of y. All right. So we'll carry out the process. I'll show you what it looks like. And then I'll show you why, in a lot of cases, depending on the nature of the function, you definitely don't always want to do it this way. And then there's some situations where you really don't want to do it this way to the point that you're willing to even convert over to a different coordinate system. All right, so 6 minus x plus 2y integrates to 6x minus 1/2 x squared plus 2yx. And that's happening over the interval of y squared to 2 minus y. So for each x value, I'm going to swap in a 2 minus y. And then also swap in a y squared. I'll zoom it out in a second. All right, so that monstrosity is what we're going to be integrating over the interval of -2 to 1 with respect to y. So this is a moment where you're like, oh, okay, cool, calculator. Got it, now I see why we have one of those. Because you're definitely not interested in doing that by hand. Math 9. Just use x's. Possibly.
Like, for, like 12 minus 6 or
Sure.
yeah, that
Uh,
means like instead of having 6
Yeah, because there's some terms that definitely could be combined. And so if you pick up on that pretty quickly, then you can do it. But I tend to let muscle memory take over sometimes. Alright, so I think I closed parens twice for some reason. Let me see if there was a good reason to do that. No, there was not. So let me get rid of that second one. And about 15.3. Or exactly 15.3, not even about, just exactly. All right, so definitely take that as a win, a much needed win, because you don't want to have to do something like that by hand. And honestly, I mean, it's not bad in terms of like the difficulty level of the calculus. It's work that you don't want to have to do. It's work. It's called work for a reason, like we don't want to do it. We have to do it. All right, so dot. It got cut off. All right, but you get your 15.3, and then you just kind of call it a day. Yeah, you can simplify a little bit, and even if I would even say if you simplify, you might be even tempted to just go the distance because it's just reverse power rule at this point. But you want to get in the habit of thinking in terms of the calculator, because if you don't, then you find yourself doing all this stuff by hand, and then you come across a problem that you really should be doing on the calculator because it just takes too much time to do it by hand, and you're not proficient enough with the calculator to get it done. So definitely take some time and practice with the calculator. All right, so number 6 is kind of what I was sort of alluding to last class, where I said that there's going to be a problem on the test that you won't be able to do one way, but the other way it'll be nothing. It'll be mere child's play. Like you're not going to have any trouble whatsoever as long as those variables are swapped. All right, so looking at number 6, this is an example of that type of problem. So you might look at it and say, oh, e to the x squared, that's not difficult. I could find the antiderivative of that with respect to x. But then I'd say, well, then by all means do so. There is a way to get it. You may remember it from last semester, like right at the very end. Taylor polynomials, Taylor series. Yeah, it's not bad. I mean, if you remember anything about Taylor series and things like that, then you come up with this integral pretty quickly, right? But if you don't remember Taylor series, except that it's a name of a thing that you learned in a course that one time, then obviously there's an adjustment that needs to be made, right? So, and that adjustment would be swapping the dx and the dy, because if I could just do that, then I'd be in great shape, right? Because all I'm doing is a function of x, function in terms of x. I'm just slapping a y on it and then moving on, right? So what I'm looking at here are x bounds, so x equals y and x equals 1. Then I have my y bounds, so y equals 0, y equals 1. So I'm just going to create a quick sketch. XY plane. So I'll do my x equals y, y equals x, however you want to define it, and x equals 1, so it's about right here. It's also saying to graph, well, it's not saying to graph anything, but we want to graph y equals 0 and y equals 1. Come on, get in place. All right, whatever, I'm living with it. All right, so the rectangular base region here, rectangular coordinate base region, but this is definitely not rectangular because we're bounded between y equals x and x equals 1 from y equals 1 down, right? So if I'm populating this space with its area, what I'm doing is I'm starting up here at y equals 1. I'm bounded by this and this, so I'm living in that interval. As I work my way down from y equals 1 towards 0, I would be creating that type of graph. All right. So that's the recipe that we're given based off of those bounds. All right. That's the base region. So you're looking at a top view of a three-dimensional system, and you're just looking at a triangular cutout of a three-dimensional solid. All right. That three-dimensional solid has a wavy surface associated with an exponential function. That's the top of it, but all the way down and into the xy plane, it's going to have a triangular shape. All right, but it's only the top of it that's going to be curved in any capacity. All right, so kind of like what is it? Kind of like one of these bad boys. Alright, so it's not fully triangular, but you know, the surface can be whatever the function defines it as, but you're going to have a constant shape to it associated with the base region on the xy plane. Alright, so the command key, I lost it. But, oh, it's only $37. Oh, I don't know what shape waves is though, so I don't know if I'm going to go that route. I didn't bring up the other images because it has the funky look to it on the lower half, but that's generally the idea. All right. So one good thing to come out of a crappy movie or a series of movies.
Wait, so the shape of
The base region.
wait, which part of the shape doesn't matter?
Was that?
The part that doesn't matter?
The part that doesn't matter is the surface shape, because that's the wavy part that's associated with the e to the x squared. Everything else is defined based off of the base region. Right, so
Kind of like a wave pattern on top?
exactly.
Or
Yeah, it could be bowed out, it could be bowed inward, it could be like sinusoidal, it could have a Superman logo on it, you know, any sort of possibilities. But the triangular base region defines what the overall shape of the column is going to look like associated with that figure. Right. So now what I want to do is swap my bounds. I keep saying bounds. Well, I do want to do that, but I want to swap my order of integration, so my variables of integration, to become dy dx. I'm still working with my e to the x squared function. All right. So, all right, that's something. But now what I got to do is I got to go back to this diagram and think about it in a different way. All right. So first, what we did was we considered what was happening in terms of the x values. It was going from the linear function over to the vertical line. All right. So we were looking at what was happening to the function in terms of x. So now let's think about what's happening to the function or happening between the functions in terms of y, right? So what I would be doing is working from, and let me just kind of clear out this diagram a little bit. Oh, the eraser's working, shocking. I think it just kind of decides when it wants to work. That's my theory. All right, so what I want to do is just think in terms of the y bounds now. So what I'm going to be doing is looking at, this is my lower bound and this is my upper bound in terms of y. All right, so lower and upper. All right, so y equals 0, y equals x. All right, I wouldn't want to say it's going from y equals 0 to y equals 1, because then I got all this extra stuff here that I don't want. That's, once I include it in the area, I can't exclude it. There's no function for subtracting an area from the base region as part of an integral, right? You can't just define it that way unless you subtract an entire other integral from it. So if I were to say that my y's are going from 0 to 1, then I would include all of this area, and then there would be no way to get rid of it using only a single integral. But if I define it as only going from y equals 0 to y equals x, I'm going to collect all of this area here. All right?
And then the next interval makes x 1 now?
Say it again?
And then the next interval makes x equals 1 now?
Exactly. All right, so the next one I'm going to be looking at, starting at, in terms of x, I want to start over at this intersection here and work my way to the right until I run out of room. Because even though I only drew the line segments horizontally and stopped at this location, theoretically, if I'm saying that the function has an area contained between y equals 0 and y equals x, I'm saying it's all of these lines, infinite distance, all right? Every single one of them, they go on forever. I gotta cap it somewhere, all right? And it would be true that they would be going in the opposite direction as well. Gotta cap it somewhere, except the upper bound was a natural capstone for it, all right? So it naturally capped it on the left, so I didn't have to worry about it. But on the right, I didn't have a natural capping, all right? So for my x values, I want them to start at this location and then work their way to the right, but then stop once they get to this location. So x equals 0, x equals 1. All right, and so now we have an integral, a double integral that we can easily work with, right? It went from impossible, not impossible, impractical, to super easy, right? So, yeah, but the thing is, you know, the instruction on this is really important, like seeing it in live action, because, I mean, you can go look at textbooks, you can see answer keys online and things like that. Look at your own notes like a week from now and look back at it, and all you're going to see is like a checkerboard in a base region. You're going to be like, okay, cool. What the hell is that telling you? You know, it's happening in live action that kind of tells you how all that information was propagated. Right. So I'm going to integrate just by slapping a y onto this bad boy over the interval of 0 to x. When I pop in an x for the y value, I get x e to the x squared minus 0, so x e to the x squared. Now, you can integrate this by substitution if you want, but you don't want, because it's a definite integral in one variable. It's calculator ready. All right, so once this calculator ready, put it in the calculator and let the calculator do the work for you. It's some multiple of e, so a rounded answer is perfectly fine. I mean, if you want, you could play around and see if you can divide out an e and math bracket, but you know, don't try too long to figure it out. Yeah. So about 0.859 approximately. But honestly, this kind of question, when I put it on a test, I don't even really look at your answer to it. I just look to see if you came up with the correct integral. Because after that, it's a question of popping it into the calculator. So, yeah, maybe I won't even ask you. I'll just say write an integral that could be used to solve this by switching the order of integration, something like that. Right? So, number 7 is along the same lines, just a little bit more complicated, and by a little I mean a lot. So we're looking for a portion of a sphere. It's actually the unit sphere that could be used. Well, we're going to find the volume of that portion of it. Now, if you could eyeball it and see, you know, just by looking at it, yeah, you're in pretty good shape. But the problem is, it says confirm your answer with a geometric form. It says write an iterated integral. So, you know, that's kind of an issue. All right. Now, it could be asking for a certain portion of the sphere, but in this case, they're asking just for the entire sphere. So geometrically, we already know the answer. All right. So you want the volume of a sphere, use the volume of a sphere formula, 4/3 pi times the radius cubed, and then just pop in the radius of 1. I mean, you could get that just by counting. I know it's hard to see, but it's 1 unit out. Right. But what we want to do is come up with 4/3 pi times, yeah, 4/3 pi would be your result. So what we want to do is learn how you would set up the integral to do this for you, all right? And then learn why you would never want to use a rectangular function integral, a rectangular integral related to a function of x, y, or z within an integral to evaluate a spherical situation. All right, because we have spherical coordinates for that. All right, if you have a cylindrical relationship, we have cylindrical coordinates for that. So we'll get to that, but for now, it's really just a matter of the skill. All right, so what we want to do is figure out what the base region is going to be. So I'll just kind of zoom in over here. Base region, that's on the XY plane. All right, that's where z is equal to 0. All right, I can solve this very easily. Square both sides. Add the x squared and y squared to both sides, and you have something that should be very familiar. This is the unit circle. What's that? Oh, it's going to be hideous. It's going to be hideous.
Is that because it's constantly changing?
It's constantly changing, but also we've got to make a double integral where the base region is defined by a circular function. All right, so there's no way it's going to be nice. You know, so I could solve this for y in terms of x. It would be plus or minus the square root of 1 minus x squared. Just kind of cut into the chase a little bit. Oh, I still have a puddle in here. So if we're looking at the graph of a unit circle, I mean, rough sketch of a unit circle. We have the top half and the bottom half. The top is y equals the positive square root. The bottom is the negative square root. So there's a couple of ways to handle this. One would be, well, it's symmetrical, so why not just work midline up? why not just work with the top hemisphere? That'll only give you the volume of a hemisphere, but then I know to double that anyway because hemispheres have the sphere. All right, so there's that. But then there's also another approach, and since we only have to set up the integral, it doesn't matter what we do, right? So I have a relationship for y that's variable related. Now, as long as I constrain the x values appropriately, I'll be in good shape. So I'll throw in a vertical axis here. That vertical axis is going to go right in the middle, but we know it's a unit circle, so the x values are going to go from -1 to 1. All right, so we have constraints, variable constraints for y, and numeric constraints for x. So when I'm writing the double integral for this, the numeric ones go in the outermost. All right, those correspond with x values, so that's going to be a dx. All right. The innermost integral has constraints that are in terms of solve for y in terms of x that go from negative the square root of 1 minus x squared to the positive counterpart. Those are y equations, or part of the y functions. So dy. And so we just have to put z in there and we're good to go. And that would be our integral. Right? Z is that monstrosity up there. Now, really, you might not look at it as a monstrosity, but I know where this story ends. It's a monstrosity. Doing this one by hand it's the definition of a nightmare, right? Because it's not really, when I integrate, it's not really a matter of swapping the bounds of integration. That radical has both an x and a y in it. So there's no way to integrate it just by slapping a y or an x on it. You have to use integration techniques like trig substitution, or maybe integration by parts or something like that. It's trig substitution, by the way. But you have to do something along those lines in order to figure out this integral. And then once you did that, you'd have to plug in these x bounds. Well, you could use a calculator at that point, but you still have to physically plug in these x bounds in order to get the thing that you need to plug in the calculator to figure out the integral over -1 to 1. Right? So it is it's just a disaster waiting to happen. Right? So this is the motivation to learn about a different coordinate system. Because if we learn to use circular coordinates in some way, then that's going to actually streamline this significantly. All right, but this is actually the double integral that would get you the volume of a sphere, the unit sphere specifically. All right, and so you can modify it pretty easily to get you the volume of any sphere. All right, so instead of -1 to 1, -a to a. Instead of 1, a squared on the inside. Sure.
When you say it's bounded by z equals to the function and the 3 coordinate planes, does that mean the intersection of the 3 coordinate planes? Wouldn't that be just 1/4 of?
Oh yeah, it would be 1/4 of it. Yeah, I missed that. Yeah, so slap a 1/4 on this and you'll have what you need. All right, so this is the volume of the entire unit sphere. Because it's bounded by the 3 coordinate planes, we would want 1/4 of it, like the diagram showed. So divide by 4 and get divide by 8. Is it a quarter?
What is a quarter at the top now? Like, steps to the top.
Then would the bounds also change to go from 0 to 1 instead of 0, -1 to 1?
Well, so what I represented here is the volume of the entire sphere.
Okay.
So we could just work off of that, but
From the diagram, it occupies like
yeah, it's a quarter of the top.
yeah,
So it's going to be
Half of the top.
But no, so
divide by 8, yeah, because this is a quarter of the top. So there's, the top is broken up into fourths, and the bottom is broken up into fourths, so it's 1/8.
Oh, we're only looking for a quarter? I mean an eighth?
An eighth, yeah. So, and divide by 8. You know, you cheat. You look at somebody else's paper. No, like legally, mathematically cheat. What you'd say is, all right, well, I did all that work and I got 4/3 divided by 8. How'd you get that? Well, I mean, you had to see the amount of scrap paper I used to get that answer, but it worked out beautifully. You know, and so meanwhile, what you did was you used 4/3 pi times r cubed. You know, so yeah, but that's not really the point. The point is that we can actually convert over into a different coordinate system and get the job done much quicker. All right, and that coordinate system is known as cylindrical coordinates. And so the conversions are pretty easy. You might not look at them and say easy when you see what's written on the page here, but since these are actually the same rules that we learned when we learned about polar coordinates, there should be some familiarity there. X is equal to r cosine theta, y is equal to r sine theta. We do have a z component though, right? Z is z, right? So what we're dealing with is a circle, unit circle with height. A circle with height is a cylinder. So we have that. So all of those rules except for the z one is all coming from that first unit. All right. So when I want to convert from one coordinate system to another, you know, they gave me, in this case, an r, a theta, and a z. I want to find x, y, and z. X is equal to r cosine theta, so 4 cosine 2 pi over 3. Y is equal to 4 sine 2 pi over 3. And z is equal to -2. All right, that's actually a fully acceptable way of representing those quantities. You just put them in as an ordered triple. You could leave it in that form if you want, but you know, like they're nice unit circle numbers, so we might as well figure it out. Cosine of 2 pi over 3 is what? -1/2. Sine of 2 pi over 3? √3/2. So -2 and 2 rad 3. All right, so my order triple, so therefore we're looking at -2, 2 rad 3, and -2. All right, that's just conversion. That concept right there is actually part of some pre-calc courses. You know, it's kind of weird to think about that or think about it that way. But you know, there's no calculus in it, so why not? You know? It's a preparation topic, preparatory. Right? So it's really just a matter of kind of looking at it in a different way. So the diagram, I mean, if we could kind of make it out, does a fairly decent job of explaining that, except, you know, getting your orientation is a little tricky when it comes to this, because really the way you have to look at this unit circle, or look at this graph, I mean, is kind of out away from it, right? So away from the paper. Here's my x-axis, my y-axis. So this is counterclockwise, so going from here over. So that's placing me, if I rotate it around this way, that's placing me at 2 pi over 3, 2 pi over 3 over here. So that's my second quadrant, right? And then we're just elevating, we're going down 2 units below the plane, all right? So you know that you're taking 2 steps toward or away, depending on whatever the x value is, the r value, 4 steps in the direction of 2 pi over 3, but then you're going down below the surface from there, all right? So if you kind of equate it to like real life, you know, you have your 0 degrees. So here's 90, here's 120. So then you're taking 4 steps in the direction of 120 and then digging a hole 2 feet deep. All right, that's where you're gonna be, right? So sometimes conceptualizing it like that can be helpful, all right? But what we're gonna wanna do is be able to convert entire functions over into polar form so that we can take advantage of the double integral process or concept in polar form rather than rectangular form. Because a question like the one that we were just working on, it's a nightmare if you had to do it by hand. In rectangular form, it goes like that if you do it in polar form, all right? So that's really the motivation. All right, converting back the other way is kind of the same idea, so I'll put a star on that. And the same idea goes for converting into function forms. All right. Typo. My example 1 should be to revisit the example that we just did, the unit sphere question. Just using this new approach. So it's just a question of I'm going to do it here or I'm going to do it there. I'll do it over here. Just steal some room. All right, so volume. Oh, hell of a question. 79. We're going to find the volume of, or under, z equals the square root of 1 minus x squared minus y squared. All right. In cylindrical coordinates. So we'll just find the volume of the entire, I'll just do a hemisphere. All right, so the volume under would be between the function and, so between z and xy. All right. So what I want to do is I want to actually convert that over into polar form. All right, so I have a rectangular set of coordinates. I want it to be polar. All right. So I'm going to pull out a negative. Oh, and sorry, polar, cylindrical, interchangeable. So I say polar and cylindrical, and I mean the same thing. All right, because all cylindrical is polar coordinates with height. All right, so if that's the source of confusion, then try not to let it be, because they mean the exact same thing. So minus x squared plus y squared. All right, so a rule for polar coordinates, just so I don't have to flip back and forth, x squared plus y squared is equal to r squared. So I want to define z in terms of r's or thetas, but not in terms of x's and y's. All right, and so after I make this slight adjustment, mission accomplished. 1 minus r squared under the radical. All right, so we won't be able to simplify that any further, so that's where we leave it. All right, but I also needed to know what the bounds were going to be for this. All right, so what we need are r bounds. So we need r bounds and we need theta bounds. So r bounds and theta bounds. So the structure, and I'll just point out the rule here. The way I have the zooming set up, it's not going to be the easiest thing to see, but we're looking at some function of r theta, or function of r comma theta, times r dr d theta, or r d theta dr. Right? So there's an extra r in there, and I'll explain next class where that comes from, because I have a proof here, but I have a better way of explaining it through actual calculus. So I think I just copied this on the internet, but I have a much better way of explaining why there's an extra r there. And it has to do with the concept of a derivative, so we'll talk about that next class. But anyway, so we need r bounds and theta bounds because my variables are r and theta, right? It's just a question of whether it's the r's that are going to come first or second. So we're going to set up our integral so that the r value is going to be addressed first. The r bounds will be addressed first and then the theta bounds, all right? The theta bounds are usually pretty easy because if I'm taking one full turn around a circle, then that's going to be 2 pi radians, right? So we're going to go from 0 to 2 pi unless you're only looking for a portion of a circle, right? But before we even get into that, what I would want to do is figure out the base region on the xy plane. So that part is no different. So what I'm going to do is I'm going to take this function and set it equal to 0 and solve. Now we already did this for the other problem, and we got x squared plus y squared equals 1. All right, we could actually work off of that, but I'm going to pretend that didn't happen, all right? Because it's actually pretty easy to solve it once you convert it over into polar form. Square both sides, you get 0 equals 1 minus r squared, which means r is equal to, r squared is equal to 1, which means r itself is equal to plus or minus 1. All right, now the negative values when it comes to r just imply direction. So the r value that would be -1 is just telling us to take a step away from a given angle, all right? It's going to turn out that we don't need the negative, all right? So we're going to say therefore r is equal to just a 1, and then that's going to define our set of boundaries, right, for r. Because we're really just working out in the direction of r from the pole, right? So 0 out to r, that's going to populate all of that space that we're looking for. Because in the form of a sketch, we know it's circular base. Oops, elliptical base apparently. Circular base. Circular base. Whatever. I'm just faking it now. All right, good enough. Whatever. I'm just talking about botching it. All right, what we're doing here by stating that r is going to go from 0 to 1 is that we're populating out our area this way now in terms of arcs with radius varying between 0 and 1. And we would do that in every direction, defined by whatever we're allowing theta to be. All right, so I shall just do it all the way around. So infinitely many circles with varying radii in between 0 and 1. All right. So what that means in terms of a double integral is that I'm looking to go from 0 to 2 pi for theta, because I want to go all the way around the whole thing. I want the whole top half of a circle, which has a base region that goes from 0 to 2 pi. All right, it's the entire circle.
So we're looking down
Correct.
at the region, not side.
Not sideways. Yeah. So it's not a profile view, it's a top view. All right. Then I'm going in terms of my r function. Now, this is the beauty of using cylindrical or polar coordinates appropriately. if you're dealing with a circular function, a polar representative of that is going to be very simple. Like x squared plus y squared equals 1 is pretty nasty, all right? But the polar equivalent to that is just r equals 1. If I had another circle, maybe not centered around the pole, you know, something centered around the y-axis, I might have, you know, something really complicated like x squared plus y minus 3 squared equals 25. But when it comes to the polar variation of it, it's really just going to be something times cosine of theta, something times the sine of theta. All right, so very, very simple. All right, so here my r values are just going from 0 to 1. And I just want to make sure that I'm living underneath the function, the square root of 1 minus r squared times r dr d theta. So this is a much, much simpler expression to work with, all right? I'll clean it up a little bit. In the process of integrating, though, you can see on the interval of 0 to 1, I have r square root of 1 minus r squared dr. It's even in this first step of the double integral, it's calculator friendly, all right? And that happens very often when you have a circular function that you're evaluating using cylindrical coordinates. All right, so math 9, r, so x, root. I mean, you can use U-Substitution here if you want, but you don't want. I don't want. Nobody wants. Ah, I hit quit. I didn't want to hit quit. Or mode, I mean. So you get 1/3. All right. Now we're integrating that with respect to theta, which, I mean, you do that by hand. 1/3 theta over the interval of 0 to 2 pi, and you get 2 pi over 3. Now, the motivation I think is there to learn about cylindrical coordinates, because you looked at what we set up in terms of the integral. I don't think you needed. It was only for half of it, yeah. So if I wanted the whole sphere, I would just double it. But you could really just imagine having to evaluate that interval on the 3 pages earlier, related to really the same problem, but it would take me a page and a half to do it. All right, so much quicker and easier. The trade-off is you have to become proficient with your conversions between polar and rectangular form. All right, so what I'm going to do is pop a star, whoever Papa Star is, on number 1 at the bottom. It's really just asking you to evaluate it in polar coordinates. So the integral is already written for you. You just have to convert it over and then evaluate it. So we'll tackle that next class.